Hello from Opava. So I would like to talk about the combination of Landau-de Gennes model, which is basic for liquid crystals, and Skyrme model for kinetic term, as you can see here. So this is standard Skyrme for order term for this curvature and F tensor. So we need this Skyrme term to recreate electromagnetism for topological defects in a liquid crystal like model. Then I go further towards the standard model using the view that model that quark strings are topological vortices. Yeah, so we need quarks as excitation of the topological vortices. So this approach is very close to Einstein's teleparallelists, who wanted to use field of four vectors to unify electromagnetism and gravity, like dynamics of this tetrad for vectors. Here are three, then finally we need four in space-time, and its dynamics, both the rotations and boost, will give electromagnetism plus gravity as Einstein wanted in the proposed approach. So let's start with electron. So electron is presented as point, but this is only a perturbative approximation. In non-perturbative, it has a field configuration, for example, of electric field. It's singular. We have to regularize this singularity. So we need to start with the Gauss law. The standard Gauss law returns charge being a real number, while in nature, this charge has to be integer. So we have to repair it. Yeah. So, and there is no way to repair it. The Gauss-Bonnet theorem, which is very similar to Gauss theorem, Gauss law, but uses this curvature. Yeah, so we have some deeper field M of, let's say, entire vectors here, and we find its curvature, and we integrate it. So this is literal integration over sphere, let's say, in space, and sphere in the configurations of this field. And with this integration, we need to have the Jacobian of this integration, and this Jacobian is proportional to this curvature. Yes, so having this curvature, if we interpret it as electric field, then our Gauss law becomes the Gauss-Bonnet theorem. So our Gauss law becomes topological charge, which is quantized. Yeah, so thanks to this interpretation of curvature as an electric field, generally the F tensor dual, we will get the quantization built in the electromagnetism, the Gauss law. Okay, so here is the final Lagrangian candidate I'm currently using. So we need this F mu e, this standard for electromagnetism, but also Jack-Mills, the Skyrme, there are very similar terms. But using this F as curvature of the field to make the Gauss law come to the topological charge. So yes, here we can see the curvature going in one direction, the second, and then the opposite. So this difference between these two paths is the curvature, which allows us, for example, to calculate the topological charge. So here, the M field is a tensor, finally, 4x4 tensor, which has diagonal as some chosen. You can imagine that shape of molecule in the liquid crystal view, or in this Einstein teleparallelism, we say that each vector field has different lengths. Yeah, so the one length is for the electromagnetism. Yeah, so this is standard. Also, in Manfred-Faber approach, this is so this N field here is this one here. Yeah, so this the longest spatial axis create electromagnetism. Yeah, so it performs the full, let's say, Hedgecock for topological defect, in being elementary charge. But then we also have this delta. So it is required to recognize twist of this long axis. Yeah, so it has much lower energy contribution, but we need to recognize it, and this twist will correspond to quantum phase. Yes, so it is related to Planck constant. So it's non-zero, but very small. Yes. Finally, we need the time axis, the zero axis in time direction, which defines local light cones. So yes, so usually it's very it's nearly aligned, but near the black holes it can bend a lot, but only in these extreme situations like near the black hole this change is larger. So we need to make that this change of this time axis is much more difficult than of spatial axis, and for this purpose we say that this length is much longer. Yeah, so it's much more difficult to bend it has much larger contribution in Lagrangian. So finally, we get this shape of molecule, the four axes of Einstein, let's say, and the lengths correspond to forces, G to the gravity, 1 to electromagnetism, this delta to quantum phase evolution, getting Klein-Gordon-like equation. And this shape of molecule can undergo rotation and boost. Yeah, so it is encoded in the O. So it is SO13 group, Lorentz group, which contains boost and rotations of our molecule. You can say the four-dimensional molecule, Einstein tetrad. So in space we have this high energy tilts for electromagnetism and low energy twist for quantum mechanics. Okay, so let's go to standard Landau-de Gennes model liquid crystal view. So in liquid crystals, they create experimentally these topological defects like His, the plus, so the molecules, elongated molecules are aligned like in the diagram. So here is plus topological charge, here is minus. And for example, they can look at time versus distance, getting some long-range interaction. Yeah, so we can see that the interaction is stronger here. So they say this is Coulomb-like. So it's not exactly Coulomb interaction, but close to Coulomb, and we'll repair it to get exactly Coulomb. Yes, so standard model I use in liquid crystals is this awesome Frank model using, as mentioned, the field of unitary vectors, and yeah, so we can enforce that the shape of this molecule is fixed, should be fixed. So this Higgs-like potential makes that this molecule want to have this shape, but can slightly deform, what will be required, especially in the center of singularities, to regularize them to finite energy. And we have this energy term, so here is the Austen-Frank, so there are various ways to choose it. But finally, in the liquid crystal society say that we should use the deeper equation, the Landau-de Gennes equation, which the main difference of that we now can recognize as twist. So we no longer have just a field of unitary vectors, but now we can three-axis. We can three-axis of the shapes of the molecule. Yeah, so we can, let's say, long axis for the elongation of molecule plus 2, defining its widths, which can be different, like here. Yes. So now we need both the kinetic term, like so here is the original one, and the potential term, which defines a shape of our molecule. Yeah, so you can say that we have this matrix, field of matrices. It's nearly tensor field, but in 3 by 3 it's a field of matrices. So which defines the three axes. Yeah, so Ni is the axes of our molecule, and they have different lengths given by these lambdas, eigenvalues. Yeah, so we have this field of matrices, which eigenvalues describe the shape of molecule and eigenvectors describe its orientation. So we like that the shape is nearly maintained. So this is done by this Higgs-like potential, which prefers some set of eigenvalues, the eigenspectrum of our M matrix, but allows it to deform. The molecule can say that you can imagine that it is elastic. So there is also a different interpretation that in fact this is only statistical description. So this deformation can be later correspond to different proportion of the molecules in various orientation. But let's imagine that this molecule literally deforms. Yeah, so this Higgs-like potential prefers some shape of molecule, but allows this molecule to deform. So there are various ways to represent this Higgs-like potential. So here is the standard Landau-de Gennes, but we could use some maybe more intuitive like this one, that there is the capital lambda, which is the preferred set of shape of given molecule, but it can be deformed into this small lambda. Yeah, so this Higgs potential want these shapes to be as close to this original molecule shape as possible. Well, here is more practical because calculation of eigenvalues is difficult, so we can get similar behavior by traces, which contains the sum of powers of eigenvalues. Okay, so here is in 3 dimensions, and now we need to go to 4 dimensions, like Einstein wanted for teleparallelism. Yes, so now instead of these three lengths of axes, we need this fourth, this gravitational, the very long axis, which is in the center of the local time axis, in the center of local light cones. Yeah, so usually it has very small changes, but near the black hole, it can have a large change. In the center of black hole, it can create a hedgehog, but it's much more difficult. So it's easy to get hedgehog for this n vector, and it should be done, for example, in every electron. But for this time, to get a hedgehog from this time axis, we would need to center of black hole. So it's much more extreme situations. Yeah? So we need to distinguish this difference between being easy and being very difficult, and it is done by this G number. Yes, very large G corresponding to length of this time axis. So like here, so here is the time axis, and our space three-dimensional rotation is the cross section of this needle-like visualization. Yeah, so we have this, instead of this standard Landau-de Gennes-Lagrange and the kinetic term, we need the Lorentz invariant Lagrange. This is not Lorentz invariant. We need Lorentz invariant, exactly Coulomb interaction, and having both Coulomb interaction and Lorentz invariant, we can get entire electromagnetism. Yeah, so and we will see later that indeed we will get Coulomb interaction for this kinetic term. Okay, so for regarding electron, so once again, we imagine this as a point, but this is only perturbative approximation. Yeah, so we can imagine that let's say apple is a point, but in non-perturbative it's some configuration of hero fields. So in non-perturbative, you ask for this field configuration, and electron at least has this nearly singular electric field. Here it's singular, but we regularize it to finite energy later. Then you have magnetic dipole moment, which is again this tiny magnet, which is a very concrete field configuration of magnetic field. Then you have angular momentum, and people try to view it in perturbative approximation that the point is twisting, but it makes no sense. Everybody knows it makes no sense, but we live in field theories, and so non-perturbative, the angular momentum is the field, not the point, but the entire field has to rotate. What is nearly the same as this magnetic dipole moment. So indeed, we should think about angular momentum being in the field, and it can be transferred into the photon, and this photon can be measured optomechanically. They measure the angular momentum of photons. So through another theorem, this field has to transfer this angular momentum and energy and momentum through photon to some different objects. Yes, so this is very real angular momentum. Something rotates there, some field, not point. So, and there is very similar related another property of electron. It's called the Broglie clock, Zitterbewegung, which are, as in neutrino oscillations, say that the masses literally propel the clock. Yeah, so they introduce the masses of neutrino for the purpose of explaining observed oscillation of neutrinos. So generally, the simplest way to see it is that in Schrödinger equation, for stationary, we already have some oscillations, but with this energy. So naively, this energy is zero for resting electron, but in relativistic quantum mechanics, this energy should be mc squared. Yeah, so we say that literally the mass of electron propels its clock. So this is very fast oscillation, like 10 to 21st hertz. So can we observe so fast the oscillation? So it's very difficult, but they managed to do it. And this is the experiment by Guarane team. So what they did, they used fast electron. Thanks of that, the time dilation made the distances between the ticks much smaller, closer to what we can observe. And so they use silicon crystal. So if then the distance between the ticks agreed with the distance with the silicon lattice, they observe increased absorption. Yeah, so there is the detector. So they have electrons, the crystal, the detector, and the question is how many electrons we will get to the detector. The remaining were absorbed by the crystal. And we can see that indeed, if they get agreement, the resonance condition between the clock and the lattice, they get increased absorption. Yeah, so there is interaction, there is resonance between the clock and the lattice. So we can say that it's also observed in the simulations, solid state simulations of Dirac equation. Okay, so here is finally my view how to connect. I'll talk later more how to connect these properties. So both the quantized electric charge. So as mentioned, I will interpret as topological charge. So the simplest topological charge is the Hedgehog configuration. Yes, but we need more. We need also these three more properties. And so what I do to this hedgehog as here, maybe let me switch to animation. I say that this hedgehog that this field recognizes the twist. Yeah, so this is not just vector field, but this vector field which recognizes the twist. And this twist for electrons should be evolving. Yeah, so if this field, this twist is evolving, it carries both the magnetic angular momentum. Yes, the field actually rotates. It also will lead to magnetic field, magnetic dipole moment, because there are very related properties. I will also mention further, and it also acts as a clock. Yeah, so this, if we, instead of just Hedgehog as elementary charge, we use Hedgehog with this recognition of this rotation, then we can get all these properties as needed for electron. Yeah, so I think this is very promising view on electron, which solves all the problems. So we need this twist as quantum phase, which evolves in this equation, but also acts as angular momentum and also leads to magnetic dipole moment. Okay, so here is this picture. What is the difference between perturbative and non-perturbative? So we can say that Apple plus Apple is equals to Apple. It's true. It's real algebra, but it doesn't say much about what's happening there. Yes, and so are Fermat diagrams. The perturbative approximation. We can use electrons as perfect points, but if you ask about field configuration, what is electric field of this electron? This is very complicated structure. So this is a valid question, trying to go to non-perturbative view, just asking for field configurations represented by given Feynman diagram. Yeah, so from one side, we can ask, having these electrons in these Feynman diagrams, what is the field configuration, its evolution? On the other side, having the field configuration, we can use its abstract representation, just as Feynman diagrams. Yeah, so these are different views. So the perturbative, with idealized, with perfect points, acting perfect apples. Yeah? So abstract apples electrons, but we can ask a deeper question. What is structure of these apples? What is structure of this field we describe in our scenario? So going to further particles, while electron oscillates, resting electron has angular momentum and generally oscillates, has the clock, what is very important from various perspectives. Also neutrinos, yes, resting neutrino also oscillates between the three flavors. Yeah, so moreover, why we think about neutrinos tiny, so yeah, so it should be the smallest, the lightest, so it should be absolutely tiny. Recently, they measured it, and this is the article that there was recoil by neutrino emission, and they can measure the energy density count, so count versus energy for various recoils. And from Heisenberg principle, we can say that the wave function is larger than 6 picometers. Yeah, so this is 1,000 times larger than nucleons. So neutrino, yes, why you can represent all the particles as perfect points, um, but but this is huge field configuration. So we can ask, what is the field configuration hidden in 6 picometers? It's 1,000 times larger than no place. So this is something very sophisticated happening there. So I will also discuss neutrino. I believe we should ask these questions. Yeah, so people try to understand neutrino only thinking in this perturbative view, but now we should finally go to non-perturbative view. What's the field configuration of neutrino? Okay, so what about quantum mechanics? So here I really recommend the series of papers. So yes, they are published in the best journals. So this is just a very small portion. There are two or three hundreds of them about classical wave particle duality objects. Yeah, so like for this electron clock, if the electron has some clock, some angular momentum, then it should also form couplet waves around. Yeah, so we have corpuscular and the couplet wave because of the clock itself. So this coupled wave is called pilot wave. And this way we get this wave-particle duality. Both the particle and coupled wave because created by its periodic process, internal periodic process, and its angular momentum. And for this kind of view, this classical, let's say, wave-particle duality view, they realize with this kind of experiments that there is a shaker and there is a oil bath and there is a droplet on this oil bath, and this thanks to this shaker, this droplet bounces to infinity, yes, indefinitely. And this droplet, corpuscular, creates waves around, which acts as these pilot waves. So here we have external shaker. Why for electron? We know that we have internal shaker propulsion, the clock. I also talk further what's the mechanism. So so, now, for example, they get the interference pattern for the double slit. Yeah, so they have the double slit, and look at the statistics of the droplets. So the corpuscular, not the wave. The statistics of droplets get the interference pattern as required in quantum mechanics. As Feynman said that it hides all the mysteries of quantum mechanics. Moreover, they got the orbit quantization. Yes, the droplet can make various orbits like here, but it has to be integer. So we can see that there is quantization, that it cannot have any continuous radius. It has to be some integer values because this couplet wave is created by this droplet has to become standing wave. So you get the resonance condition like in stationary Schrödinger equation. Yes, the couplet pilot wave has to become standing wave. They also got double quantization, both of the radius in vertical axis, and in horizontal axis there is angular momentum. Yes, and there are some trajectories they observed. Yes, also a lot can be obtained for classical objective wave particle duality. And electron, if we understand the clock, its proportion I'll talk about, we also get we should also get this coupled wave, which allows to get this quantum-like phenomena like here. Also recently they got the CHSH relation Bell-like, yes, so the Bell relation provided, so also can be done. In this article. Okay, so let's go to solitons. So here are one-dimensional solitons. So in the conference I didn't have to present it, but maybe in the video let me do it briefly. So here is the simplest one-dimensional soliton, which we can build. Literally, there are these mechanical models. Also on the soliton there was such attempt. So I think it's a very educative tool to get such model. So so as you can see, you have a set of pendula which are coupled by this spring inside. Yeah, so both the pendula would like to be down, but also they want to minimize that tension, the distance between the two neighboring pendula. Yeah, so mathematically we get this kind of equations, this wave-like equation with potential, gravitational potential. This sign is saying that for given angle you are down. So this is gravitational potential. Yeah, so you are now, and by 2 pi further you are still down. Yeah, so here is one down, here is another down. And between them we can make this kind of transition. We have one down to infinity and one down to plus to second infinity, but still is a mass. So this is a like particle. It contains energy. To release it, we would need to collide it with opposite, with antiparticle. So we have this king, and there are anti-kings, and why there is this maximal velocity massless radiation like photon, so it can travel with the speed of sound here instead of speed of light. So the massive are limited by this, so they can only approach this maximal speed, propagation speed. But here is resting king, here is traveling king. We can see it's much narrower. So this is literally Lorentz contraction. We have the same equation as special relativity. So this is very simple model, mechanical model. There are some videos on YouTube you can check. It creates a lot of physics like quantization. We have one king, two kings, three kings, which are created by pair creation. You cannot just create one, you have to create both two, like electron, positron. And and entire special relativity. Also the time dilation for breeders. Okay, so let's go to more complicated situation from one-dimensional to three-dimensional. And there is this well-known analogy between electromagnetism and hydrodynamics, which are governed by nearly the same equations. With this mentioned this main difference that one is uses speed of light, one uses speed of sound. Yeah. For example, they even get in these droplets they even get analog of Zeeman effect, yes, which sounds very quantum. But in this analogy, the Lorentz force used for Zeeman effect becomes Coriolis force. We know well from mechanics. Yes, like here is such video. So here's the dimension the orbit quantization. So we have now two droplets which rotates like here. And now we rotate the entire bulb, and you can feel about the centrifugal force, and so it's intuitive that they change distance because of Coriolis force, what corresponds to Lorentz force in electromagnetism. So literally in this article here, they get this kind of Zeeman splitting, that you can split this quantized orbits up or down depending on if it's clockwise or anti-clockwise rotation using Coriolis force as Zeeman force. So there are many more nice effects in this analogy. For example, there is well-known Barnett effect, that even if you have object without charge, if you rotate it, you can create magnetic field. Yeah, so we don't need charge for a magnetic field. So again, yeah, so this argument may be also for electron that it doesn't have to use the charge. The magnetic dipole moment of electron doesn't have to use the charge. We only need rotation of the field itself. Okay, and finally, for example, there is this well-known relation between this velocity and the quantum phase, and this A field using electromagnetism. So they are very similar. Both the velocity and the A field is very similar to quantum phase, also having some this rotation-like interpretation, but now multiplied by this h bar. Yes, it has different contribution. So quantum mechanics seems very similar to electromagnetism, but with different contributions defined by this Planck's constant. I will mention also further. Also, there is this Aharonov-Bohm analogs in hydrodynamics. I recommend this article, which was suggested by Michael Barron. Yes, also they get similar behavior for electron and for hydrodynamics. So in the article there are two, but they look very similar. So I just place here. So okay, so we have this similarity between electrodynamics and hydrodynamics, especially for superfluids. However, now we miss the particles. Yeah, so we have the electromagnetism, but what are the charges? So now we can get the charges, as mentioned, as topological defects, and they do it experimentally in liquid crystals. They create these topological defects of these configurations of molecules, and look, for example, time versus distance, and indeed they get long-range interactions. They say it's Coulomb-like, also getting different powers, some annihilation. So in various scenarios, they can get various long-range interactions. So it's very close to electromagnetism, but misses exactly the Coulomb interaction and Lorentz invariance. So now let's repair it to get exactly electromagnetism. Yeah. So maybe before let's think about another topological defects we also get in liquid crystals. So one unavoidable is this point topological defect, for which they get Coulomb-like interaction. So natural interpretation is as elementary charge. We would like to get a simple model of electron, let's say. And they have topological vortices. Yes, they call it discrimination in liquid crystals. So we need these kind of structures. They are called because of vortices in superconductor, superfluid. Also, we need it in liquid crystals. The question is, what do they correspond to in particle physics? And turns out they are well known required for quark strings. That we have quark anti-quark, and they are connected by this one-dimensional structure required for corner potential. I mentioned in a moment to get this attraction, this confinement of quarks, why they cannot escape. Yes, so that first they can freely be. So yeah, so Yeah, so they can escape of high energy. They can freely move. So to get both, to get the quarks in this view, this topological view, we need both the topological vortex as the quark strings, and now we need quarks, which are fractional charges. Yes, in standard model. So for us, charge is this hedgehog. Yes, like here. So how to combine the two types of topological defects? We can do it like here, that we have this vortex, but now we rotate the field inward, outward. Yeah? So if we do rotation by pi, you would get a hedgehog here. So you would get elementary charge. But if you do pi third, then you have 1/3 of elementary charge. Yeah? So while there is charge quantization, we can get fractional charges. However, you can see that there is something wrong going between them. Yeah, so there is some conflict which needs some regularization. So it will have some energy approximately proportional to length of this distance between quark and anti-quark. Yeah, so this way we get this confinement, you can say, for quarks. So we can bend, let's say, the charge quantization, but at cost which is proportional to length of this fractional distance between these fractional charges. Yeah, so this energy of quark string. Okay, so I'll talk further about it, and finally, having these quark strings, there is to model LHC collisions, they use so-called string hadronization. Yeah, so this is the basic model they use for collisions. So they say that in the collision there is created this quark string, and now it decays into particles. Yeah, so if you assume, so if you ask what is this vortex from non-perturbative perspective, from this field configuration, then the only answer I have found in literature is as topological vortex. So we can say that this is topological vortex. So to find the correspondence, we just need to look what they see in LHC collisions, what is what are the final particles, and what topological vortex can decay into. Yeah, so we have to compare them and find which topological excitation structure corresponds to which particle. Yeah, so I will talk about it further. Okay, so here are some arguments why we should treat these topological vortices serious, not only in superfluid superconductor, but also in vacuum. Yeah, so there are considered mainstream as cosmic strings that there are some one-dimensional topological defects in cosmos, but maybe there should be also closer to us, let's say. Yes. So, and in Sun's corona, they indeed observe these one-dimensional shining lines, and they don't really understand why there are lines, why they don't dissipate, but they stay stable lines. But there are some suggestions that they might have topological nature. So finally, going to smaller physics, as mentioned, we need them for quark strings. So they are usually assumed to be only inside baryons. But if they are inside baryons, the one-dimensional structure, why they cannot go outside? And I think there are many arguments that they do. They go outside. They help with nuclear binding between nucleons. And the best argument, I think, there are halonuclei, like lithium-11, that it has a core and it has two neutrons in very large distance, like 5 femtometers. This is like 5 times more than of nuclear force. So it shouldn't, the nuclear force shouldn't longer work, but still they are binded, and it's for milliseconds. It's a very long time from nuclear scale. So what binds them? So I think natural answer is that this topological vortex quark strings goes out of this core, and literally we have these bits on this necklace. Yeah, so topological vortex can go through these two neutrons, which help to bind them. And if you want to effectively describe it, you need three-body forces. Yes, and they indeed require three-body forces to describe nuclei and more nuclei. Okay, so the question is why we need effective nuclear three-body forces. So using this one-dimensional structure indeed would lead to such necessity. Okay, so let's think about these topological vortices. So here are in superfluid superconductor are because of vortices. And here is this mentioned in of quark string.
So yeah, so here is from this ring. So here is quark, anti-quark, and there is some conflict between them, and it has a lot of energy between them. Yeah, so this energy between them grows linearly with distance. So finally, then there is the potential they use. So for Cornell potential, first we have Coulomb interaction, then we have linear behavior, asymptotically. Yes, linear because this energy between them is linear, approximate. So, how to get it with topological view? So, as mentioned, we need this for quarksing. We need topological vortex, and we need to add quarks as fractional charges. And for us, charge is a hedgehog, so we need to perform a fractional hedgehog like here. So 1/3 of this road to the hedgehog, but it leads to this conflict, which will have which gets some energy per distance, like here. So this way we get the Cornell potential that first we have Coulomb interaction, but then wanting to take them apart, there is this conflict of linear energy per length, so we get asymptotically linear dependence. Yes, so we just get picture, just got Cornell potential, which is as part of QCD LHC simulations. Okay, so here are these halonuclei. I've mentioned that we have this core and two neutrons, or it can be also proton, one proton, two protons, one neutron, two neutrons. They call them Baryon, that if you remove one, then the second will fall apart. Yeah, so will go away. So this is very magical, you can say, if you don't. So they have effective description, and these effective descriptions require three body forces. So two body forces are not sufficient. So what binds them? So here you can see the minimum of nuclear potential. It's like 0.8 femtometers, while here we have 5 femtometers. So they shouldn't be stably binded, but they are experimentally. So I think the only answer to non-magical, non-perturbative, so that we're not guessing, but there is some structure, there's some field configuration. The only possible answer could be this topological vortex. That indeed this line should represent quark string being topological vortex, which goes outside here and goes through them. So finally, we should think about nuclei maybe not as these grapes, maybe, but later as really knots of the quark strings being non-perturbatively being topological vortices. Yes. Okay. So what about spin? Yeah. So here are the topological defects in 2 dimensions. So if you have a cross section, for example, of this topological vortex, then you can get these kind of configurations like this or this. So that you go around such topological defect, and the field rotates here once, here also once. The difference between them is the global phase. So we can say that there is gouged transform. Here the field rotates minus once. Here the field rotates twice. And here the field rotates 1/2. Yeah, so you can see that if you perform 2π rotation, the field rotated by pi. But you use a field which is the same after pi. Yeah, so you can say that this line and this line, if you don't distinguish the arrowheads, they are the same. Yeah, so and in liquid crystals you have ellipsoid-like molecules which don't distinguish if it's in this orientation or this orientation. So in liquid crystals, this kind of configurations are very, very popular. And they have this topological charge 1/2. And this 1/2 is in agreement with quantum rotation operator that rotating spin S particle by theta angle, the phase should rotate by spin times theta. Yes, and this is exactly what's happening here. So this is in agreement with the quantum rotation operator. So I believe this is we should interpret this cross section, this two-dimensional topological difference as spin, while for three-dimensional, this point-like, we should interpret them as electric charges. They get Coulomb interaction. Okay, so let's go to the Gauss law, as mentioned at the beginning. So we have this standard naive Gauss law, which is great, but has two problems. One problem is that it can get any real number, while in nature should be integer multiplicity of elementary charge. Second problem is the infinite energy of point charge. We also repair later. So here is the reparation of the lack of charge quantization, that we can have used the topological version that integrating curvature, some curvature, and we will get generally this 2 pi n times Euler characteristic, but we can use it for fields of unitary vectors, let's say, and we get for these n fields, we have to define the connection, the Christoffel, so how the field rotates if you go in given direction, and then the curvature. And now we can interpret this connection as the A field in electromagnetism, curvature as F tensor, dual. So I forgot it should be dual all the time. So if I don't use dual, then I will get magnetic monopoles for the topological charges. So if I use dual, I will get electric monopoles. Yeah, so that's the distinction. That's the question. Do we have magnetic monopoles? So there are people searching for magnetic monopoles, but all the searches are unsuccessful, and they expect that they were created after Big Bang, but we don't observe them. So maybe the problem is that they forgot about using dual formulation. Yeah, so there is a freedom. We can use one or the second. So we need topological defects that are required. The question is, do we interpret them as magnetic monopoles or electric monopoles? The mainstream interprets them as magnetic monopoles, but they are not observed, but we observe electric monopoles a lot. Every electron is electric monopole. So maybe, so the simplest answer to the problem is just switching to dual formulation. And now all of them, the magnetic monopoles they search for are just electric monopoles, electrons. Yeah, so they search for something abstract, but maybe they already see them. Why they are everywhere, like electrons and other particles, such particles. Okay, so here is some view of pair creation. So here we have nothing, but assuming that we have energy to get to this configuration, now we have plus topological charge and minus topological charge. Yeah, so we can see that the farther they are, the larger tension of the field. So it literally corresponds to this Coulomb interaction. Yes, but because here the tension is much stronger of the field, so the field would like it to go back to this to make them together and annihilate finally. So in the moment we get Coulomb interaction this way. So we can also understand on this picture the virtual particles pair creation at least. So that to really create electron plus positron, you would need a lot of energy, 2 times 511 keV at least, to create electron plus positron. But we could start this process having some smaller number of some amount of energy. Yes, we have like 100 keV energy, so we could go, let's say, here, but then we would have to go back. Yeah, so we started perturbation of the field toward pair creation, but had to go back because we don't have enough energy. So in Feynman diagram, in perturbative pictures, we would need virtual particles. But in field configuration, yes, this is just going here, that's field configuration and going back. Okay, so here is this calculation numerical of Coulomb interaction between the topological quantized topological charges using this source from Mathematica. So here are the two configurations. Here are the opposite charges, opposite monopoles. Here are the same monopoles, and the colors visualize the energy density. And so here is maybe let's go briefly to the source. So here is the ansatz. So it's approximate, but quite good. But finally, it should be optimized. Matthew Faber does it in the next slide. Then we assume the cylindrical coordinates. Then we define the matrix. I would like to work of the matrices to finally be able to recognize the twist. And here is this sum of curvature square Hamiltonian, as mentioned, we need. And here we integrate it with a cutoff. So here we remove balls around the singularities. If we don't do it, we get infinite energy. Yeah? So here we use the cutoff. I will say in the moment how to repair it. And this way we get the dots. So the dots and then the lines are fitted 1/r Coulomb interaction, and you can see that it looks perfect. Yeah, so this is simplified calculation, but you can see that indeed we can get 1/r, 1/r distance potential, which is effective potential, and in agreement with Coulomb. Yeah, so we just got Coulomb potential by integrating Hamiltonian as energy of configuration for various distances of opposite or the same charges. Okay, but I mentioned about the singularities. So without the cutoff in the center of singularity, we would get infinite energy. Yeah, so there is a big problem. So there is discontinuity, and the derivative would go to infinity. So we need to repel it. Yeah, so how do we do it with this Higgs potential? Yes, I have mentioned that it's required that, let's say, this molecule has some shape, but it need to be able to deform. To remove the singularity in the center. Okay, I have also shown here. Yes, so here you can see that the molecule has the form from elliptic, which is preferred energetically by this elasticity of this molecule, this Higgs potential here, and it's deformed to the spherically symmetric to avoid singularity in the center. Otherwise, you'll get discontinuity, you'll get infinite energy if we wouldn't have this spherically symmetric configuration, configuration in the center. Okay, so yes, so we can use Higgs-like potential, for example, here literally Higgs. So it prefers unitary vectors. So usually there are unitary vectors. It's called vacuum dynamics. Usually we have this vacuum dynamics of unitary vectors, which will give us the electromagnetic plus quantum mechanics plus gravity. Also, it's called Gaussian bosons, these masses dynamics. But in the center of singularity, we have to activate the Higgs potential. Yes, otherwise we get infinite energy. So this way we can see that there's some deformation. Yeah. So and if we from a charge perspective, this deformation corresponds to that. If you integrate energy of electric field of charge, perfect charge, you will get infinite energy. To get mass of electron, you would have to integrate from approximately 1,4 femtometer. And so this is quite a lot. So you need a deformation distance of a few femtometers, in fact, to not to exceed mass of electron with its energy of electric field around. So finally, all the energy should sum to the mass of the particle, like for this kink I have mentioned. So finally, we should. So as Manfred, we should get the total energy of this configuration as exactly the mass of electron. Yes. Okay, so if we include this deformation, it will also deform Coulomb interaction in very small distance. Yes, and Faber has performed this improved calculation. So like this optimization of field configuration, not just using ansatz, and the Higgs potential. So you can integrate down to the center of the singularity. You don't longer have to use these cutoffs. So if you do it, so Manfred has do it with him. So you can see that the dots gets stronger force than Coulomb. Yeah, so you can say that the alpha controlling Coulomb, the alpha becomes larger. So we have a running coupling. Yeah, so and it is not known experimentally that for very high energy, the alpha grows like for electron like to 127 in 90 gigaelectron volts. Yeah, so this is observed experimentally that indeed the alpha increases for very high energy. And so and Faber has shown that this known from running coupling deformation agrees with what we get. Yeah, so that this regularization we need not to exceed mass of electron with its energy of its field alone. Gets exactly what we need for the running coupling. It seems the same. So we should think about electron as point-like, but not exactly perfect point charge. Perfect point charge would have infinite energy. We need to deform it to finite energy, and this way we get the running coupling known from experiments. Okay, so here are some experimental boundaries for size of electron. So how to compare it with textbooks, and textbook usually say that electron is practically a point, so the size can be large. So if you take a look, search for the arguments they use. The basic argument is the G-factor argument, which comes from the Delmet's article, 1988 article, who has this kind, which gets this kind of plot. So this is the main plot that they use. So here you can see the G-factor -2 versus radius for three cases. So one case is triton as made of 3 nucleons, proton as made of 3 quarks, and versus here hypothesis of electron being made of 3 partons. So nobody has want any partons. We just want to deform. So here we just want to deform perfect point charge because it would have infinite energy. We just want to regularize the infinity. So nothing about partons. And what's happening here? So you can see that if you draw a line between these 2 points and go to here, you would get negative. So naive extrapolation will give you negative radius for electron. So what Delmet did is drawing a parabola. Yeah. So if you want to extrapolate from 2 points with parabola, you can get any value you want. So it makes zero sense. It's completely nonsense argument, but everybody uses it. So please think about it and maybe take a look at that. So let's think about more serious arguments. And there is the most serious, I think, is the electron-positron cross-section. So here are the plots for log scale. So we have huge energy, like hundreds of graph here. So we can see in the log scale, there is a line. Yes, so there is a line, plus there are resonances corresponding to some particle equation. But we are interested in not in size of high energy electron as you have Lorentz contraction. It becomes pancake no matter what configuration would be the initial. We are interested in the size of resting electron. So we should extrapolate this line to the mass of resting electrons positron, 2 times 511 keV. If we extrapolate this line, we get approximately 100 millibarns, which corresponds to like 2 femtometers. So this is exactly the size we need to deform, not to exceed mass of electron with energy of selective field. Yeah. So this is in perfect agreement, I think. So electron is point-like, but not perfect point. Perfect point charge would have infinite energy. This is some more sophisticated. We need some regularize it, and this regularization from one side is observed here. This extrapolation to resting is in agreement with this regularization finite energy. And as mentioned, the running coupling also. If we had a perfect point charge, we wouldn't need any deformation of Coulomb interaction. While in nature we need to increase alpha for very, very high energy, very low distance. Okay, let's go further. So I have talked about this dynamics of three axes, Reper, Dreibein, I to say, but finally fundamentally in fourth axis. Yeah, so we get Einstein's tetrad. Yeah, so we have this teleparallelism Einstein approach in dynamics of 4 axes. So the 4 axes in space-time we'll have both the rotations as mentioned. So there is this long axis, it has tilt, high energy tilt, and low energy twist. And it also there are boosts. Finally, the dynamics form the SO13 Lorentz group. So now we need different energy contributions, and we can see it, for example, in QED Lagrangian. In QED Lagrangian, you have both F mu for electromagnetism, but also H bar C, very tiny contribution of quantum phase evolution. Yes, here is derivative and hides quantum phase inside. Yes, so we have two contributions of these dynamics of very different scale. This is like a very small contribution. So here I can represent it with these different lengths. That we have this one long axis, but then is also this tiny axis. So this twist is recognized, but it has very tiny contribution. Yes, it should correspond to this H bar C. So very tiny contribution of the twist corresponding to quantum phase. And then we need to add the boost, which has huge contribution. So now to bend this time axis, it can only be done in practice near the black hole. Yeah. So usually, why this twisting is very fast and frequent. This one is only this hedgehog around the charges, like electron. Why to make a hedgehog of this zeroth axis, you would have to be in the center of black hole. So it's very difficult. So it's easy to rotate the two relatively, but to rotate the long axis is very difficult. So the contribution in Lagrangian for gravity should be huge. Yes. For this dynamics, and we will get something like that in a moment. So generally for this boost, we'll get second set of Maxwell equations analogous. Yes, you have one vector for the describing rotations in space and one vector of gamma tilde describing boosts. And we will get another set of curvatures. So we have curvature for standard curvatures and curvature for gravity with tilde. And we have also this kind of cross curvature between electromagnetism and gravity. It describes the coupling between electromagnetism and gravity. And here we have various types of coupling. Yes, we have so the basic one known for general relativity is that we need that in gravitational field the electromagnetic propagation will be slowed down. Yes, if giving slowing down of electromagnetic propagation in gravitational field, we get both the light bending from the Fermat principle and the time dilation, because all the chemistry is made of electromagnetic propagation, so everything would slow down. Yes, it has something like that, but then we have also different type of coupling I will mention later. Additionally, besides this vacuum dynamics of this rotation of this tetrad, we have also changes of length of the axis. So this is much more difficult to get. You need only, it can happen only in the center of the particles. So only for regularization of singularities. So yes, like shown earlier. So we will get some additional interactions, type of interaction, which act only very close to particles. And this is well known as weak-and-strong interaction. So I believe this deformation of the shape of this ellipsoid should correspond to Yang-Mills, gluons, weak-strong interactions. Yes, so we get finally by the dynamics of this tetrad, by rotations and boosts. By rotations we get electromagnetic quantum mechanics. By boosts we get gravity. And by deformation of length of the four axes, we can get the Yang-Mills, the some short interaction. So we can get unify the model. Okay, now let's go to the clock mechanics. Yes, I mentioned that we need for electron that resting neutrino already oscillate. How to get it in the field theories. And mathematically, we can easily do it. And with the term which will appear automatically in the model I'm considering. So okay, so here is standard phi model with the king. So like here we have one vacuum, the minus one is minimum of this potential, and the plus minus is also minimum of this potential. So this is standard king, but now we add this kind of term, minus curvature square. So I mentioned that I need curvature square terms in Lagrangian Hamiltonian for Coulomb interaction and for magnetism. But now we need with minus. So we see that indeed we will get this minus later in the full model. So now let's think about toy model, this one dimensional. So now this term with minus, it has both the phi one is spatial derivative of the field building the particle. Yeah, so it's only non-zero in presence of particle. And now we have psi zero. This is this quantum phase time evolution, time derivative. So this it has minus. So it allows to reduce the energy of the particle. Yeah, so it only acts when you have phi one non-zero. What is only true in the presence of particle. It allows to slightly reduce the energy by starting oscillations. Yeah, exactly what we need for electron and neutrino, for example. So then finally the energy depends on this frequency like this that you can have standing king, but it's not global minimum of energy. So energy can be reduced with this term slightly, not a lot. So it can be only slightly reduced by activating these oscillations. Yeah? So the particle indeed activates oscillations to slightly reduce energy its mass. Yeah? Okay, so we get the clock propulsion toy model in this moment, and now let's think about the complete model. So here is my complete Lagrangian candidate. So now you have this F mini, but if 4 indexes. If you have standard F mini in electromagnetism with 2 indexes, if you go from Lagrangian to Hamiltonian, you get only positive contributions. However, if you have 4 indexes, going from Lagrangian to Hamiltonian, you get also negative terms. Yeah, so you cannot avoid negative Hamiltonian terms if you use the full 4 index F, which is curvature for us. And full curvature indeed has four indexes. Yeah? So if you use full curvature as F, then you cannot avoid negative terms Hamiltonian. And there are very subtle. It's difficult to activate them. Usually, if you try to do it, you also increase energy more. Yeah? They only like here only could allow slight reduction of energy of particle by activation of oscillation. But this is very subtle. If you don't do it in such a way, then the field could go to minus infinity probably. And so if you want to activate it, you also have positive contributions. So you can only slightly reduce the energy. These mechanisms have to be very, very, very careful. So if you do it, so here is our full F mini. So in Hamiltonian, there are squares of these terms. The red terms are squared with plus. And here you can see them. This R1 is the curvature we need for electromagnetism. This one is we need for the quantum phase evolution for Gordon equation for quantum phase. This one for gravity. Yeah, so here you have the sum, and now and finally energy is the square. So we should get square of this one. So for electromagnetism plus square of this one for gravity, but also the product. But they work in completely different scales. Yeah, so gravity changes very slowly, while electromagnetism changes a lot. So this product is practically negligible, should be practically negligible. So we can treat them as separate electromagnetism with gravity, plus some coupling, but very, very subtle. But the more important is this coupling. The blue terms have negative contribution in Hamiltonian. So now there's minus curvature square. So as here, yeah. So we get minus curvature square terms. So now these minus curvature square terms have both the gamma tilde, which corresponds to boosts, and the gamma ones, which can be zero. If mu is zero, then means some rotation with time. And so the oscillations we need. Yeah, so it can literally brings energetic tendency to both add the rotation, the clock, and add the gamma tilde, the boost, so local boost around massive objects. So that means the gravitational mass. Yeah, so naively, so while we have the charge quantization as elementary charge because of topological, for gravity there is no gravity quantization. The mechanism is much more subtle. So literally, we need some. If we don't have a mechanism, then there would be no gravitational mass. The zeroth axis would be just aligned perfectly. There would be no need for it to bend. So we need like this term to make it energetically preferable to slightly bend this time axis to get the gravitational mass of particles of larger objects. So this is absolutely crucial to explain gravitational mass. So these terms, these negative terms in Hamiltonian explain both the time derivative can reduce energy by adding this time derivative, so the oscillations, but also requiring the boost. Yeah, so both the mass and the clock. Yeah, so we get the more subtle dependence between the mass and the clock, as also in the Baryon clock or in the neutrino oscillation mass frequency dependence. Okay, so now let's go to the particles, assuming these three axes. So, for example, we can perform the hedgehog using first axis, second axis, or third axis. Yeah, so we get three types of hedgehog, which topologically are the same, so have the same charge, but need some slightly different regularization. Yeah, so what's happening inside is different, so they will have different energy, different mass. Yeah, so we get three charges of different mass, like three leptons. Yeah, so we could go from the heavier ones to the lightest one. So the muon and tau can decay into electron, but they could for some time can be this excited state of electron, you can say. Yeah, so we get the three leptons, and moreover, we can understand why there are no naked charges. Yeah, so electron needs also magnetic dipole moment. So this is a very difficult question. Why there are no naked charges? Why there is no naked electron without magnetic dipole moment? And here we can understand it because if we have the three axes, if we perform Hedgehog with one axis and try to align the second axis, there's a problem. There's this Hilbert theorem that they have to be singularities at the sphere, and these singularities correspond to magnetic dipole moment. Yeah, so we need some singularities. And the Hilbert theorem allows to explain why an electron cannot be just spherically symmetric in its has to have also magnetic dipole moment. Yes, so okay, so let's go to the version 3 hadronization that they believe in LHC collisions that there is created quarks. They use models that there is created a quark string and it decays into particles. And if we ask what this quark string is from non-perturbative perspective, the only answer I have seen in literature is the topological defect. So we need to find the correspondence between what topological defect can decay vortex can decay into and what they see in LHC collisions. And for example, topological vortex can decay into a simple loop. Yeah, so we get this kind of loop, but we have three types because we have a loop with one of the three axes along. So as we live in three dimensions, there should be three types of these basic types of loops. Yes, and moreover, so they will be very stable. And we can oscillate. We can rotate the field from one to another. Yes, so we have three very light, very difficult to interact with objects. Yes, neutrino is much more stable than the photon. Yes, photon cannot pass to Earth, neutrino can. Yes, so we need to understand why neutrino field structure is much more stable than a photon. To be able to penetrate Earth, for example. Yes, so with this kind of structure, it will be very difficult to interact with, but possible. So okay, so we get natural candidate for neutrinos, and as mentioned, experimentally, it turns out they are huge, 6 picometers, so 1,000 times larger than nucleus. So yes, these kind of loops could be huge. No problem. They can be very light, so they don't have the central singularity which require to equalize all three axes. We only need here to equalize two axes, which is much cheaper. Yeah, so they can have very light. They can be very light. So we get finally some candidate for neutrino, and we can also have knots. So here are some basic knots that we have one vortex in the center and second vortex going around it. Yeah, so we cannot avoid it from decay of quark string as topological vortex. And if you look at this interaction, the vortex around deforms the configuration inside. And it deforms it is exactly toward the hedgehog. And hedgehog for us is topological charge, elementary charge. Yeah, so if this hedgehog is enclosed, we get a charged particle, so like proton, but if we would like to get zero, we would have to compensate it, -1/3. So we can just explain why proton is lighter than neutron. So now it should be the opposite, but if we see that the structure of baryon due to this interaction requires some charge, let's say 2/3, then proton can just enclose this charge, neutron has to compensate it, yes, explaining why neutron is heavier. And also, neutron has positive core, negative shell, what is known experimentally, I'll show you in a moment. Okay, moreover, such loop like here could also have internal twist like here, yeah, so like Mobius strip or more. And if you think about the knots, with adding this internal twist, then we get good agreement with the decay of strange baryons, that they can change the stages by one by producing a pion, so this would be pion here, and or by two by producing kaon, so double rotation would be kaon. Yeah, so it seems that we can naturally get strangeness at least by just twist of the external. Okay, so let's go to this baryon. So as mentioned, we need in string hadronization we need the vortices, the knots of vortices. And the simplest knot is like this, not one vortex around another. And it leads to this deformation, which in this interpretation of charge as topological means that this is some positive charge, which can be enclosed by proton. For neutron, it has to compensate it. So we just explained why proton is lighter, because it just encloses. Neutron has to because compensation is costly. And here we would have the 6 quarks that we have the 3 types of quark strings, but they can have the loop around like here, or they can be without. So loop around gives tendency for this 2/3 energy, while without we have to compensate the required charges. Yes, so this way we have 6 quarks. Yes, three quark strings because of living in 3 dimensions, like for neutrinos, and 2 times 2 because there is vortex around or not. So now we can also understand why the 2 matrices are so different. So CKM matrix says how it's difficult to change between the quarks, and this PNMS matrix says how it's difficult to change between neutrinos. For neutrinos, it is relatively trivial. For quarks, it's very difficult. It's much more diagonal. So geometrically, we can see that it is easy to go between one neutrino to another because we have just to rotate the field. We can relatively easy to do it. But for quarks, they are in the knots, and to rotate the knots, the field inside knots is much more difficult. Yeah, so we try to rotate one, we would also have to rotate another. So we can now understand why the CKM matrix is much more diagonal, because for knots it's much more difficult to rotate the field. Okay, so here is the mentioned charge configuration known for proton, for neutron. For neutron, it's not just 0. For neutron, it is believed that it has positive core, negative shell, and we just got it. Yes, positive core because of this interaction, neutron has to compensate with, and negative shell of this compensation. Yeah, so we just got very non-trivial thing, which is known from experiment. And moreover, if you think about the deuteron, so we got 2 baryons, and each of them has this tendency for charge. And we can get like this. It can be symmetric. It has plus, minus, plus. And plus, minus, plus is a quadrupole moment. So experimentally, it turns out, indeed, deuteron has a large electric quadrupole moment. So that's a very non-trivial fact, because if you think about proton and neutron, naively, there shouldn't be a quadrupole moment. Yes, with just plus and 0 shouldn't give quadrupole moment, but it is, and this picture shows why you should get it. So I think it's the simplest example of so-called EMC effect, that thinking about nuclei, we cannot think about just a bag of quarks. It's much more difficult. The quark structure, it is known, is completely different when nucleons form nuclei. Yeah, so, and here is the simplest example that naively, deuteron shouldn't have a quadrupole moment, but experimentally it has. And in this picture, it should have, yes, because baryons require charge in this picture because of this interaction of the 2 vortices. Okay, so let's think about the neutrino for a moment. So it has to go from beta decay. So if as mainstream says, if baryon requires some topological vortices, then if there is energy released, for example, in beta decay, 782 keV difference between neutron and proton plus electron, it has to be released somewhere. So some could go to this topological vortex, this quark string, and if it forms the loop, it will be a neutrino. Yeah, so indeed, part of energy from beta decay could go into the topological loop, which is interpreted as neutrino. Yeah, so you have 3 types, very light and stable, oscillating. So as mentioned, there is mechanism, so I don't have the details, but yes, it should be worked on. Generally, I need help to calculate the details, so because they are quite difficult. So I need some serious numerical simulations. They are difficult for me to do. So we can think about energy conservation. So naively, if you think about neutrino oscillation, so you have 3 neutrinos at different masses. The oscillation between them would violate the energy conservation, naively. Yeah. So I always had this problem, but here you have no problem, because if you rotate from between different flavors of the vortex loop, then there is change energy density per length. So to conserve energy, it can just change the length. So it suggests that during the oscillations, also the length is changed. Another problem is the sterile neutrinos so they need them for some and so suggestion here is that if you have, let's say, this beta decay, some configuration of this field of flavors are preferred, and to interact back there is more sophisticated dependence to this probability of reverse process. Yeah, so capture of neutrino is. So you need to get proper parameters. Yes, again, there is a chance to explain it here, but simulations are very difficult. Okay, so let's think about some general problems of standard view on nuclear physics. So, for example, quarks, in fact, correspond to only to 1% of the mass in the standard model. Here, indeed, the quarks are, let's say, just this tiny configuration, while the entire energy is in this complex configuration around. So indeed, this could be just 1%. You can interpret it as a very tiny percent of mass of the energy of the particle goes with the charges around. Then the spin crisis, that they wanted to get the spin only from quarks, while here it is, while we know that only 40% is in quarks. So indeed, here the entire configuration can rotate, so it's much more complicated. So indeed, the gluons, I would say, this is the deformation of the field. So mostly here there are lots of gluons, you can say. So indeed, the spin, the mass is not in the quarks just, but in the entire configuration of the field. Proton radius passes. So if you probe a proton with electron and muon, they get different radii. So it is easy to explain because qualitatively, because a difference between electron and muon in this picture is rotation of the field by pi. So it should have some slightly different interaction. There is neutron lifetime puzzle that cold neutrons have slightly shorter lifetime than hot neutrons. So it suggests that neutron has some internal excitations. Yeah, so it's more complicated. So for this structure, you could excite it and so find the difference between slightly excited neutron and unexcited. Yes, so this cold and hot neutrons. Then this EMC effect, that if you try to think about larger nuclei as just back of quarks, it doesn't work. It's completely nonsense. So here is the predicted line, and here is the experiment. Yeah, so when nucleons bind into nucleus, the quark structure completely changes. Yeah. So, and the example was, as mentioned, getting a quadrupole moment for deuteron. Naively, it shouldn't be. While we get it, and in this picture we also get it. Okay, so then these bosons, we should think about some dynamical configurations. Okay, so I believe we should indeed think about the evolution, some dynamical modes of the field, some rotations we could interpret as bosons by going to Feynman diagram, but it's very difficult to do it right. So it needs to help again. Okay, so here is the summary of them. So here is the basic topological charge for which they experimentally got Coulomb-like interaction, while we have repaid to read Coulomb, then having these three axes, then we can get the types of hedgehog, the same topological charge as electric, but different mass, so like T leptons, also requiring this singularity kind of magnetic dipole because of the heavy Bohr theorem. Then we have three types of topological vortices, like for a loop for neutrinos. Then we have knots, which seems in a good agreement with baryons, and then these baryons can be nuclei, like the halo nuclei, which could be bound by this quark string as topological vortex. Deuteron gets the quadrupole moment. Radius could be explained by this internal twist. And released the kind, I think qualitatively it seems to agree. Then the part of energy of beta decay could go into neutrino. Okay, so maybe let me skip so here is then some calculations of the two gammas for the rotations and boosts, so we can get the curvature, the gravity magnetism. So here are the three plus topological charges. Here are the anti. So we can say that one of them are electrons, and one is positron, or the opposite. And I think there's freedom here to choose. So here is the curvature. If you include the length of the axis, so we can see that there are these different energy contributions. So the lengths indeed say that we need three different energy contributions, at least in the Lagrangian. So one is for electromagnetism, FPN, for quantum mechanics, like this QD, we need this H bar C, very tiny contribution. And for gravity, we need huge contribution to make that making Hedgecock for electron is much easier than Hedgecock for gravity in center of the black hole. Yeah, so we need and here it is expressed by this capital gamma describing this length, the preferred length of the axis. Okay, so here is again some energy contributions and the uniaxiomatic the case for the Mann field. So if we use the matrix field as just using one, so you can say that the eigenvalues are 1, 0, 0. Is 1, 0, 0. So here is fixing the second one to 0. Then we get this Mantel-Faber approach as he got, but the difference means using non-zero, this gamma tiny one, but non-zero, allowing to recognize the twist corresponding to quantum phase, getting Klein-Godel-like equation. Okay, so here is the Lagrangian again. So here are the three levels you can say for electromagnetism, that we have the electromagnetic field, but it is said they are not fundamental. The people say that A field is more fundamental because, for example, the Hartmann-Bohm effect. While here we say that we need even more fundamental level because those still allow for charge being any real number. While nature should be integer number. So there means charge quantization. To get charge quantization, we need to make the Gauss count topological charge of some deeper field. So we need to introduce this deeper field, like here, which unifies the quantum phase. So we can say the rotation, that in the momentum operator, this gradient is rotation, but this is also derivative of this deeper unified quantum phase, you can say. And topological charge is calculating this quantum topological charge of this long axis, but there's also topology of the twist 2π central for quantum mechanics. Yeah, so here we have the field as the diagonal, our shape, and applied the rotations and boosts, and this field undergoes here we have the curvature. Yeah, so we go mu and the opposite we subtract, so we get the curvature, which also can be seen as a Jacobian for integration of infinitesimal elements. And we use this curvature as our F-tensor with 4 indexes. And so these 4 indexes lead to this Hamiltonian with sums of squares of these terms. Those are with positive contributions, getting electromagnetics, quantum mechanics, gravity, but also this very supple coupling with negative contribution Hamiltonian, which allows for the clock and for the gravitational mass, which without this kind of explanation, we would have a 0 gravitational mass. So this is crucial because we don't longer have the topological charge quantization for gravitational mass. We need some additional energy description why it is preferable energetically to get the gravitational mass for particles. Okay, so maybe some very briefly some mathematical calculation to assume that here is the Euler-Lagrange for this view, and finally we got the three Euler-Lagrange equations for the three rotations in space. So here it's very close to Maxwell equations. You can represent them in a simpler way. And here is Klein-Godel-like equation for the twist. Yes, the quantum phase gets Klein-Godel-like equation. Okay, so here is for the Hedgecock ansatz. So again, you can find that this Klein-Godel-like equation for Hedgecock like electrons. So it's a bit special. So it looks very complicated, more complicated than the standard. So probably some averaging should lead to the standard Klein-Godel-like equation, but it needs further work. And it's for gravity. Now we switch the spatial rotation to 0 and just look at the boost. and we get very similar Maxwell-like equations. So again, we get the Maxwell equation for gravity, which are called gravity electromagnetism, and with coupling, they can also get the if we get slowing down of electromagnetic propagation in gravitational field, then we get slowing down of clock made of chemistry and light binding because of Fermat principle. So here is again the clock. So they are called such objects, field configurations are called time crystals, and they are very popular recently. That resting particle have a tendency to oscillate. Yeah, so the pendulum doesn't have. The pendulum you can slow down to zero by minimization of energy, but for time crystals we like that resting already has some oscillations, and we need it for electron, for neutrino, and as mentioned, you can obtain it with these negative terms, Hamiltonian negative curvature squared terms in Hamiltonian. But in presence of particle here, yeah, so this is spatial derivative of shape of the particle of its field. There appears a tendency for quantum phase evolution. So the particle can reduce mass energy slightly by activating oscillations. And finally, this is the last slide. So this is standard modeled. So it's huge and it looks like Taylor expansion. So when it didn't work, they just guessed another terms and so on. So it looks like kind of model epicycles. And moreover, this is for perturbative approximations. Yes, imagining electrons, particles as perfect points created by creation operators. Moreover, there are also probability distribution hidden in the Dirac terms. Yeah, so they use wave function which hide the probability distribution. Fundamental models should not have probability distribution. So where to find a fundamental model which have the particles as real configurations, and then after Feynman averaging, we should get effectively the Dirac terms and generally this standard model Lagrangian. And as I explained, this kind of approach seems very promising for these approaches. So it extends electromagnetism, Yang-Mills terms, Skyrme terms with built-in charge quantization for electric charge as topological, because the Gauss law counts the topological charge. And from vacuum dynamics, just this rotation of this Einstein tetrad, we get from rotation, we get electromagnetism plus quantum phase, so electromagnetism for tilts, quantum phase from twists, and from boost we get gravity, we have the electromagnetic approximation at least, and from topological defects we get the particles, especially with point-like charges as electric charges and vortices as quark strings, which are pushed up to building baryons. And hopefully effective description of this field, if you include all these types of excitations, and hopefully we'll get close to something like standard model. I'm searching for collaboration to go further. Thank you very much for the attention.